In this video, we're going to look at the nature of the atom and how it interacts with light. And we're going to start off focusing on light and some important discoveries about how light truly behaves. This has led to some really important discoveries and some evidence that needs to be explained by the nature of atoms, and really has built towards our modern understanding of atoms that has really held up pretty well over time. These are focused on quantization of energy, which we can get from principles like the conservation of energy that we've talked about a lot in this course already. As we look to understand the nature of the atom and how the electrons reside within the atom, it's really important to take a step back and think first about the nature of light. And we start by thinking about the photoelectric effect, which was a major finding by Einstein that demonstrated that when we shine light onto metal, electrons are ejected, but only when we use certain frequencies of light. And as it turns out, it doesn't matter how much light we use. What matters is what type of light is used, whether an electron is going to be ejected. And this has some really important significance. And the first of these is that it was hypothesized that light isn't just like a wave as we think about it, where it has crests and troughs and it can add together and it can refract, which is all things that light does, but that it also exists as particles called photons. And it's these particles that are interacting with the particles called electrons that we know are already part of the atom. And secondly, we see that the energy of this photon is only dependent on its frequency or wavelength. And something like the brightness of the light that we're shining on, that does matter in that there are more light particles available, but it's the energy of these individual particles that actually determines whether or not an electron is ejected. This laid the groundwork for a lot of insights into the atom that we're going to see moving forward. But before we do that, let's think about these photons. So what we've come up with this is that the energy of a photon is first directly related to its frequency. And we'll talk a little bit about these terms here. And secondly, that the frequency and the wavelength are inversely related, and that together multiplied, they are equal to the speed of light. So these are the constants that are here. If this seems like kind of a lot, I might consider looking a bit more deeply at light, but we're going to kind of go through this rather quickly, because what we're really going to look for is the relationship of these photons to the atom. So again, frequency of light, this is like how many crests you see. So if we're watching waves on a beach, we see crest, 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 or a higher frequency, we might see crest, 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 crest. And the wavelength is the distance between the peaks. The speed, when it comes to light, is a specific value. That's how fast the wave is traveling towards you. And Planck's constant is what ties together the energy of a photon and its frequency. And so here, just to think about these things, you can think about these equations, you can think about what you know about light already, but pause the video here and think that based on this, if the wavelength of light increases, so if the space between the crests gets larger, what happens to the energy of a photon? Go ahead and pause and see what you think. All right, conceptually working with these equations is really important. When we have the wavelength increase, what this means according to the second equation is that the frequency is going to decrease. So if we have the wave crests further spaced, then we're going to see fewer of them per second. And if the frequency decreases, then the energy must decrease as well. So higher wavelength, longer wavelength means lower energy. Shorter wavelength means higher energy. Okay, before we jump into the atom though, try a little bit of practice. So go ahead and pause the video again and see if you can calculate the following here, right? Try the first one, that's probably the most straightforward, then the second and the third. See if you can come up with the answers we show in a second. But again, just go ahead and pause the video and see what you can do to start. All right, hopefully you were able to put up a good attempt at these. So for the first question, 615 nanometers is the wavelength. We want to know the frequency. We basically want to say, well, let's use equation 2, right? The speed of light is equal to the frequency times the wavelength. Let's make sure that we're putting our wavelength into meters, as that is the unit that the speed of light is given in. If you want to convert the speed of light to nanometers per second, you will absolutely be able to solve correctly as well. and we get that the frequency is 4.88 times 10 to the 14 per second. We see that many wavelengths, crests of light per second. That's because the wavelengths are a small value, right? 615 nanometers is very small, and it's traveling towards us at 3 times 10 to the 8 meters per second, which is the speed of light, very quickly. What about the energy of this photon? So we already know the frequency. Can we go from there? Well, yes, we can, right? We can say the energy is directly related to the frequency. We've calculated the frequency above. It's the same wavelength that we're dealing with. And so using Planck's constant, we see that the energy is equal to the following, something on the order of 10 to the negative 19 joules. And this may sound like a really small amount of energy, but remember that this is one photon, one particle of light, which is on the order of matter of an electron. So a very small amount of matter has a very small amount of energy. Not really matter, right? A very small amount of, light, right? One individual particle of light, and it has this very small amount of energy. So what about the last question? What is the wavelength of a photon with a given energy? So kind of tying it all together. You can combine these equations, but I think that one thing that's missing from that is that the first equation is really specific to light and a particle of light, whereas the second equation is more generalizable towards speed and waves in general. If we used, instead of c, the speed of, the waves in the ocean coming towards us, that would be totally fine as well. So taking one equation with a major restriction and combining with a more general equation leaves us with that restriction. So I think you can go ahead and solve it this way, but if you want to solve it in steps, go ahead and solve for the frequency based on the energy, and then solve for the wavelength based on the frequency. That is totally fine as well. Here my solution rolls it all together, and we end up getting that the wavelength is 2.17 times 10 to the negative 15, or 10 to the negative 5 meters, and there we are. So hopefully you're able to get a good answer for that. Calculating wavelengths, energies, frequencies of photons, definitely very important. Okay, so what about the atom? Let's get into the atom, and specifically the Bohr model of the hydrogen atom. So the Bohr model states that we have a positive center and that there are specific energy levels, stationary energy states, as we go away from that nucleus. And for the sake of the Bohr model, we're going to name them n equals 1, n equals 2, n equals 3. These are higher energy orbits as we get further and further from the nucleus. Now, no energy is radiated while an electron is within this stationary state, so it's kind of like a stable track. An electron can just stay on n equals 2 or n equals 3 or whatever. But if it should go from one state to the next, the atom can change from one stationary state to the other by absorbing or emitting light. So basically, if an electron should absorb light in n equals 1, it might jump to n equals 2. We can use the following equation, therefore, to say, well, if there's a photon that's being absorbed by this atom, by an electron in one of these energy states, then it's going to gain energy. And the amount of energy that it gains is equal to the energy of that photon, which we've shown how to calculate previously. This is conservation of energy. It's very important and kind of a universal concept in science. And we can use it here because if we know about the energy of light, we're going to make conclusions about the energy of this specific atom. Okay, so why is this so important, and what kind of got us to this place where this is an accepted model for the atom? And we're going to talk a little bit about the limitations of the Bohr model coming up, but it does have a few really great achievements, and the most notable is it explains this hydrogen emission spectrum. So basically, if we take hydrogen, the atom hydrogen, and we excite it and we let it relax, we're basically making those electrons energized, and then when they fall down to a lower energy level, they will emit only certain wavelengths of light because the energy levels in the hydrogen atom are only specific distances apart. We see only these 4 bands when we excite and allow hydrogen to relax. And this corresponds to transitions within the hydrogen model, right, within the hydrogen atom. Now, if we could be at any energy level we wanted, then there would be a continuum. There would be any amount of energy could be absorbed or released by the atom. But it's constrained only to these very specific bands, and it's all hydrogens that do this. And they're very sharp, right? We don't have like a little bit of variance. They only release specific energies. So what is the significance of this? This is the transitions between energy levels within the hydrogen atom. And it shows not only are these electrons bound to these certain energy levels because the transitions are bound to certain values, but that all hydrogens have this same value, right? All hydrogen have this same specific transitions for these specific states. And so this experimental data is sort of what needs to be explained. And this idea of the Bohr model, that there are only specific tracks on which the electrons can have energy-wise, it does explain this hydrogen emission spectrum. Okay, but Bohr is not perfect, and as we're going to see further on in this course, we do need to have a lot more than this n equals 1, n equals 2, n equals 3 orbits style picture, because the Bohr model only really works for hydrogen. You know, if we have one electron, this works great, but if we have two electrons, then they would be interfering with each other, and this really doesn't take into account that interference. And again, you know, with this model, we basically say the first electron would add to n equals 1, and then if that's full, then we'll add to n equals 2, and if that's full, we'll get to add to n equals 3. But if we have like a bunch of electrons, and we know that beyond hydrogen, there are many, many elements that have more than one electron, you know, most elements have more than one electron, this Bohr model really breaks down. So we need a more complex model to describe all atoms in general, and we'll look at that very soon. However, it is really important to take from Bohr that this idea of the quantization of the energy, that there are definitely tracks and energy levels within the atom, you know, because of that hydrogen emission spectrum. This becomes later better understood, but for now, accepting that idea that we have specific energy levels that the electrons live in within the atom and that it explains the hydrogen emission spectrum is really a big success of Bohr and is an important lesson to take with you to the next video.